Alright, so we're looking at concavity. Right, so in here from A to B, it's increasing. Do you remember we talked about increasing? Mm-hmm. Yes. And then at B, it switches to decreasing. Yes. This would be known as concave up. This would be concave down. Okay, so that's just a little bit of a feature here. So a region in which the gradient is increasing, the curve is concave up. If the gradient is decreasing, it would be concave down. So that's just summarising what it says up above. A point where the concavity changes, so from concave up to concave down, but doesn't necessarily pass through a stationary point, is called a point of inflection. Okay, so as I say, concavity is coming up more and more. Whether it comes up in yours, I know, who knows, but anyway. So we know that the derivative is the rate of change of the function, yes? In other words, we know that it's talking about the gradient of it. Okay, so the rate of change of the y with respect to x. The second derivative is the rate of the change of the gradient. Okay, so it's how does the gradient change? We know that when the derivative is equal to 0, that's when stationary points occur. And we know that when the second derivative is greater than 0, it's a minimum. And when the second derivative is less than 0, it's a maximum. Yeah, so we've talked about all of those things. If we're trying to find if there is a change of concavity, what we do is we find the second derivative, solve for, put that equal to 0, and solve that value. Then we look to the left of it, we look to the right of it, and see what has happened to the gradients. Or yeah.
So the change in the concavity is what's up and down?
Yes.
Oh my gosh. Miss Harrison, you want me to write for you? I think you need to do your thing again, Miss Harrison. It's back on
for a few minutes. All right. Okay. So we double differentiate. Okay. So here, this is our function. f(x) is x to the power 4. Derivative, 4x cubed. Lovely jubbly. Second derivative, 12x squared. Okay. So we put that second derivative equal to 0, and we solve it. Lovely. Our value of x is going to be 0. We look to the left of it, we look to the right of it. We're going to substitute this value into the second derivative. Okay? So if we substitute -1 into here, we get 12 lots of -1 squared. -1 squared is 1 times 12 is positive. We look to the right of it, 12 lots of 1 squared. We've got 1 squared is 1 times 12 is positive. Because this is positive and this is positive, it means that the concavity is concave up and concave up. So that means that there's no change in the concavity, so this is not a point of inflection. Do we see that?
So what would that look like?
What would what look like?
That if you sketch a line that's going that way.
What would it look like?
Because it's one of my flashes, it's like a bam, 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 bam.
So one of these kind of look like that. So we're talking probably oh, I don't know.
Would it look like a cloud?
Just like that. Well, let's. I guess we could sketch what it looked like.
Okay, put it in our calculator.
Yeah. Group effort. Right, 5x to the power 4, 20x to the power 3. So we've got our second derivative. We put that equal to 0. Oh, funny enough, we get 0 again. But when we stick 0 into the little table, again, we're looking left and right. We know the second derivative is 0, but the second derivative in this case would be -1, a -20, shush. And here it would be positive 20. So because it's gone from negative to positive, or concave down to concave up, then it is a point of inflection.
I'm saying anytime it's to 0, it's going to be 0. Right. So you're always just
No, not always. It just so happens that this one is at 0. So if we had solved, if it had been more complicated, so for example, if it had been x to the power 5 plus 3x squared or something, and we were finding the second derivative, but it would be more complicated. It just so happens I was doing something basic.
Oh no, fabulous.
Yes? Right, so these are just snipped from from a textbook, just because I think it's quite nice explanations that I could have watched by myself. So we know second derivative concave up. When it's a minimum point, it's concave up. When it's a maximum point, it's concave down. Where the concavity changes, it's a point of inflection. So a point on the graph is an inflection point if the second derivative is 0 and the sign changes. So you have to have both of these two features. So you could find that the second derivative was 0, but that doesn't necessarily mean it is a point of inflection. Now, let me just go back to the notes we were filling in the other day when we first talked about the second derivative. Oh no, I need to go even further. And of course, now it's outline again. Remember, here. So I've said, here it was maximum, here it's minimum, here you need to investigate. Okay, so if it is equal to 0, it is usually a point of inflection, but it's not always. So you do have to check that there is this change in concavity before you start saying yes, for sure it's this point of inflection. This is a nice little diagram here. So this is concave down, concave up. So this here, because it's changed from concave down to concave up, then here would be a point of inflection. Yeah? Lesbians? For the functions from example 22, it doesn't matter where they're from, I use the second derivative to find the intervals where the function is concave up and concave down, and find the inflection point. So, here's our function. So, we're differentiating it. Okay, you've got it in front of you. Differentiate again. We put that equal to 0. Okay, so the second derivative is put equal to 0. We solve that, make it x is 12. Okay, because this would be 12x equals 6. X is 6 over 12, which is 1/2. Okay, look a little bit to the left of it. Look a little bit to the right of it. Here you would find that the second derivative is negative. Here it would be positive. And so it is a point of inflection. And so because on this side it's negative, which way around is it? It's concave down. Okay, so it would be concave down all the way to the left of a half. Okay, so they're saying from negative infinity up to a half is concave down, and from a half up to positive infinity, it would be concave up.
Can you draw it down? Yeah.
So here's
Did you look at me? I didn't do that.
That was a please help me.
Why is it so far up?
But why did that one go there? So at the point where it's a half, then, I mean, I don't know what this graph looked like. It's a cubic graph, but that doesn't really make much difference. So it's concave down all this way here.
Oh, okay.
Okay.
Concave, yeah.
And then concave up. Oh, far out. It's concave up from that point.
Yeah.
Yes? Yeah?
How raised the top ones too?
They were too high up. I'm really struggling. Oh, having a laugh.
These expressions though, Miss Harrison.
Okay. So we knew that it was a point of inflection, so then they just stuck the value of a half into it to find its partner. Okay, because they actually want the coordinate of it. Lesbians? Second example. So we've got x squared minus 4 over x minus 1. Oh, do we believe that the second derivative is 6x over that? What rule would we use to differentiate this bad boy?
Oh, yeah.
Okay.
Product.
Two people were kind of having any recollection here.
No, I do, because product is the other one. Product, that's when you multiply, right?
It's when things are being multiplied, yes, Tristan. Okay, so we've used the quotient rule here and got this value here, and then we've differentiated it, found the second derivative, and got this bad boy. Okay?
Yeah.
So there's a practice for you if you're not sure and you would need to practice that, then maybe you want to practice that. Should we do that together?
Yeah, I think we
I
should.
don't know.
Do you have space around yours?
No.
I think we should do it. Practice.
My back.
Oh,
Did you call it out? My back.
I could have found a hard enough tennis ball.
well, that actually worked. Right, so then we've got the second derivative, lovely jubbly. We're going to put the second derivative equal to 0. Now, if this is equal to 0, then we would get rid of the denominator, yes, lesbians, so that we're just left with the top, rearrange that, lovely jubbly. Now, when we square root this, what happens?
You can't square root.
Good, you can't square root a negative number, so there's no real solutions. Okay?
I didn't even see it in line there.
You didn't see this negative? Did you see it on your page in front of you? Okay, that's okay, as long as you can see it somewhere. But here we can talk about when the second derivative is undefined. Okay, so we would focus on the bottom. What does undefined mean? Well, that was in functions chat a long time ago. It's where, asymptotes. It's undefined, there is no value, and we know that things have no value when. But what makes what makes something have asymptotes?
When the x goes
When the
Denominator is a square. Zero.
Okay, when the denominator is 0, it would be undefined. So they focused on that portion here. Okay, so if we rearrange this bad boy, we find that the value of x is positive or negative 1. Okay? So from either side of negative 1 and positive 1, we've got a negative second derivative, we've got a positive second derivative, we've got a negative 1. So is there a change in concavity in between these?
Yeah.
Negative to positive, positive to negative. Yes. So there's two lots of change in concavity. So it's concave down on this side, concave up here, and concave down here. Okay? So what are we now asked to do? Oh, okay. Lovely jubbly.
Mm-hmm.
Are you kidding?
The last example was just x cubed. Okay. So first derivative, second derivative, put that equal to 0. Solve it. Look to the left and right. Concave down on the left, concave up on the right. Because there's a change, it's a point of inflection. Okay? Does that help? Right. Okay, so given that the graph shown is a graph of f, sketch the graphs of f dash and f double dash. Oh, yes! Now, this is a slightly different thing. This comes up another time. Let me pause this.